and then I'll do a little demo of the I2C connection to the to drive an LCD display. So that's what we're doing. And I might even start by taking attendance. Who knows? Be a good thing. It looks like we're having a die-off among 1343ers. So I'll give a few minutes for the last stragglers to roll in. Okay, so if we pull up the syllabus, and we look, so that's what's on the docket, 4.4. Serial protocols, I2C, SPI, and others, and a demo I2C. So that's what we'll do. And then this lab, oh, I guess, is that, I guess it is I2C with LCD. I haven't actually looked at it yet. Let me just pull that up and make sure. Has anybody looked ahead at the lab? Is that what it is? I2C with, okay. Yeah. So, yeah, I'll have to make sure we have the I2C, the LCD displays and stuff down there. Yeah, okay. I don't know how many LCD displays I have with the I2C thing on the back. I may have to fix that. There were a bunch of them that just got demoed, and so I'm not sure how many are left. So, okay, let me list them real quick. I'm glad I noticed that. I'll check that out. Okay, so here we are, labs. Okay, so lab 10, I2C with LCD. Okay, yeah, that's great. Okay, so yeah, all right. So I'll go over this. So yeah, so it's yeah, and it turns out so notice that there's two of these I2C LCD. One is R I2C LCD, and the other is I2C LCD. And the reason there's an R I2C LCD is because the people who make these little buddy boards that go on the back of the 2-line-by-16 LCD displays come from different manufacturers, and some of them actually make them differently with pins connected to different pins on the I2C parallel chip. And so, as a result, you have to change the way you send information to the display down the I2C line because it won't line up correctly depending on which one of those you're using. And so one is the reverse and the other is the normal. And so you have to make sure you're using the right one. And I think we have those instructions relatively clear, but I'll double check that. All right, that's great. So that's basically, so that'll be sort of, so you'll see what we're doing. Maybe I'll start with the demo, because that's always yeah.
When is the project going to be used again?
No, so I made an announcement in class. We did move it. It is on the 18th.
Okay.
Yeah, which is good, right?
Yeah.
Yeah. What was it?
Well, I knew that I suspected this was going to be a problem. Okay, so I don't have my. I seem to have lost my cable, so I'm not going to show you. I'm not going to go through the code directly. I'll do it kind of indirectly, but I'll just show you how this works and talk about it a little bit. So here's the. So here it is, and I think this is. Oh, something didn't plug. Oh, yeah. And then it takes a minute before it comes on. There's some delays and stuff. And something else must be recorded. Oh, that makes sense. Okay. Now, still takes a minute. No. So it just prints out ABCD and it keeps going and it scrolls around eventually. But you saw the hello world on the lower line, right? Okay, so the way this is working, if you look at it, on the back of this, we have just 4 wires connecting, okay? Let's dial in a little bit. Maybe we'll even turn on one. So there are 4 wires. There's power, ground, SDA and SCL, and then there's a little pot. The pot takes a fine Phillips screwdriver. So if you have a Phillips screwdriver, you should bring it to class. And you can tweak your pot a little bit, and that changes the contrast to make it really readable. So this is pretty well adjusted, but when it's not set for 2-line mode, it wouldn't be adjusted right. So if you're going to run it in 1-line mode only, then you should probably mess with the pot and get it tuned in for that. If you're doing 2-line mode, then you can do that. So notice there's a little board here, and it solders onto the pins directly on the back. So it's connected to the pins. It's connected to all the connections on the LCD display, and you can see all of them are labeled real nicely across there. So ground, VSS, power, VDD, and then there's this VO, that's the contrast pin, and that's what this little pot on the back here adjusts for you, so you can set the brightness. And then there's RS, RW, and E, the three control lines, and then there's the 8 data lines, of which we only use 4, and the other 4 are grounded through resistors, I think. And then the last 2 pins, A and K, and that's the A pin is power and the K pin is ground. So the 2 outside pins, 1 and 16, are ground, and the next 2 pins in are power. And that's for the backlight. And there's a little gizmo here on the back, a little 2-pin jumper right there, where if you pull it off, it takes out the backlight. So you leave that on if you want to see the backlight. The display's still working, but the backlight's just not there. And you can see it. It's just writing, incrementing the position through the display. And of course, because it didn't write, it went from P, and then QSTRJK, whatever, I did it wrong. I have a little trouble with the alphabet from time to time. But anyway, when it went through Z, then it switched to symbols, and then finally it got around to lowercase stuff. And by the time it got to lowercase I, it's coming back around and printing on 40. So between 0F and 40, it dumped all those other characters into the display memory, but they're not displayed because it's only 2-line by 16. It's not 4-line by 20, which would include all the display area. Okay, so there's the demo. So let's look at the code. You go on Blackboard, and you go to Blackboard and to the course, and scroll down. And then you go down to lab. Well, actually, you don't go down to lab. You scroll down till you get to LCD files. And this LCD instructions are those 2 articles by Julian Eilert that you really should read, especially if you're going to use an LCD display in your project. You definitely need to read those. Anyway, if you're just going to do the lab, you should look at the LCD files, although this is all on the thing. So the parallel interface, where you have to use a total of 6 or 7 wires, that's all set up here in these 2 files, a header file and a C file and a header file. But the I2C, 4 wires that you have to hook up, power and ground, so really only 2 wires that you have to connect to your board. And those 2 wires could actually be used to drive other things. You could read a GPS module. Well, the GPS modules are usually set up with UART, so it probably wouldn't work for that. But you could definitely read a whole bunch of other stuff that's I2C compatible. The actual chip that's on there, I have trouble reading it. I might have to have somebody. Well, maybe I can read it. Actually, you might be able to see it. If we can really scroll this down. It's a PCF. I always forget the numbers, but actually, I may be able to read this one. Yeah. So this is PCF. I think it's 4574. 8574. Yeah. And that particular chip comes in 2 versions. The 8574, and then there's another one, and I forget which one that is. Let's see. So I think there's an 80, let's see if there's an 8576. yeah. So the interesting thing is, it's the same thing. It's a universal LCD driver for low multiplex rates. Oh, well, actually, maybe this isn't the right chip. So. Yeah, yeah, I think it is, actually. But anyway, I don't know. I think this has some extra stuff on it. Maybe if I go back to the other data sheet. Where is it? There's the PDF. So, yeah, okay. So they give you PCF 8574 and PCF 8574 alpha. And the difference between the 74 and the 75 alpha is that they have different hardwired addresses. So the 8574 varies from a slave address of hex 20 to hex 27, and the alpha varies from a slave address of hex 38 to hex 3F. And so that gives you the ability to have 16 of these chips on the same I2C bus if you want to, and give them all different addresses and everything will work just fine. So you could have 16 of these. And it's basically, what it basically does, it takes the I2C input here, the SCL and the SDA. SCL is the clock line for the I2C protocol, and SDA is the data line. And it allows you to basically write and read 8 bits of parallel information from some other device. Now it's kind of weird because the inputs are not buffered. So you have to, so the inputs, so the way this works, these outputs are open collector outputs. So what that means is there are pull-up resistors on them, pulling them up, and all you really do is pull them low. So when you want to read, you let them all, you set them all to all the output bits to high, and then if the external circuit pulls it low, you can read that, basically. So it's kind of a weird thing. It doesn't really latch those in like you would really like. So it's not a true parallel interface in that sense, but you can definitely use it to get data both directions. It's just that if you want to read, then you have to make all the pins high. At least I think that's correct. I'm pretty sure that's what it says. Yeah, bidirectional parallel bus expander. Well, anyway, I don't want to get bogged down on that. But basically, that's the chip. And so this is really a nice little chip. If you want to use an I2C chip to have 8 bits of parallel interface to control a bunch of, maybe you want to control a bunch of LEDs or who knows what you want to do, you can put a bunch of these chips on there and you can have a whole bunch of lines you're controlling. And you can read them or you can write them. So it's very nice in that regard. It's a nice little chip. Okay, so that's the chip that's on there. And then that chip then is connected to the LCD display, and the only other thing it has, I wanted to show you one more feature. So if you look at it, you see there's these the 3 little areas here called A0, A1, A2. So those connect to the 3 pins on the PCF 8574? Yeah, 8574. It connects to the PCF 8574 and sets the 3 bits of address that you're allowed to set externally. So the chip is hardwired from this chip 20 slave address hex to 27. But those last 3 bits can be set, and that's how you can pick it from 20 to 27. So you can have it be 20, 21, 22, 23, 24, 25, 26, and 27. And that's nice because it lets you have multiple chips. The problem with it is that unless you know how these are actually set, you may not be sure what slave number to give your device when you're trying to talk to it, and it can drive you a little crazy to begin with. All right, and so anyway, so this is continuing to do its thing. It also went into I guess I cycled power. So, and that's bad. It's like that. But anyway. All right. And, okay, so anyway, so there's that. Okay, so in this case, almost all the ones we have, if you buy them commercially and you just solder them into your 2-line by 16 LCD display, they'll either read hex 20 or hex 27, and usually nothing in between. But you can set them usually for anything in between that you want. But they usually come out of the factory set one way or the other. All those address lines are either tied high, and then you have to pull them low, or they're tied low and you have to, or they're pulled low and you have to tie them, and you have to tie them high if you want. And they usually have little solder pads for you to do that, but not always. Okay, so you have 2 header files and a C file. So let's look at the header files briefly. So this file, this is a generic I2C driver, and you can, if you want to use some other I2C enabled device, you can use that driver directly with any I2C device. It should work fine. So we'll open it with WordPad, hopefully. And then we'll do, so that was the generic I2C driver, and then we'll get the I2C LCD driver. And then we'll get the C code. And then we'll talk about those briefly. Okay, so I wanted to show you the I2C driver first. So what this is, I stole it from High-Tech C, but actually I had to modify it. But I left this on there just to be fair. So it's pretty well modified. And so a couple of things. Some chips label these things differently. If you wanted to use, so our chip has, well let me ask you, how many serial modules does our chip have? You don't know? 2. That's right. And they're labeled 0 and 1, I believe. They might be 1 and 2, I forget, but I think they're 0 and 1. So this is already written. It's hard coded because of these lines for the one module. So if you wanted to use the other module, then you'd be out of luck without having to go in here and change all the references where it specifies synchronous serial port 1. You'd have to put in synchronous serial port 0. And then notice synchronous serial port 1 con 1, con 2, synchronous serial port 1 address, synchronous serial port 1 stat. So all those registers would have to be changed to synchronous serial port 0 stat, or if it's 2 stat, I forget which one it is. We can check that at the end. All right. So, and the way it's set up is it's hard coded also to use the RB4 and 6 pins. RB4 for SCL and RB6 for SDA. Now I actually not sure about this. Let's see. I guess I. So if I go down to the data sheet, so if we look at the data sheet and we go to, we look at this screen here. So this is the synchronous serial port screen. Now, because the synchronous serial port can be programmed as an SPI or an I2C port, then you have a bunch of choices. You have slave select, and you have serial data out, serial data in, and serial clock. That's all SPI. And then SCL and SCK, that's all I2C. So you sort of have to keep in track those names, and then of course you have to remember that RX and TX, that those happen to deal with the UART. So it can be kind of confusing what's going on here. But in any event, since we're looking for SCL and SCK, RB6 is SCL1, and RB4 is SDA1. So, and it is 1 and 2, it's not 0 and 1. So here's SDA2 and SCL2. So actually they all seem to be coming out the RB port. And you can look at these and notice on these there aren't any if you have a little note in parentheses, then that means this is reprogrammable using the APF-CON 0, APF-CON 1 registers. But these are hardwired to these ports. So your only choice then for the I2C line is RB4 and 6 for 1, and RB5 and 7 for 2. Yeah. So interesting. All right, and then you can also use them, but notice the slave select line can be reprogrammed. The serial data out to line can be programmed. The serial data in line 1 is there. The serial data in line 2 is there. And the serial data out to can either be here or here, and you can set that in the APF-CON register. And then the serial data out 1 is there. So you kind of have to, and the slave select one's there. So some of them are fixed. Some of them are you can switch between a couple of pins in the APF-CON 1 and CON 0 registers. Okay. So if you go to the serial data module, so it's the SSP synchronous serial port, which is master synchronous serial port. MSSP1 and MSSP2. And if you look at it, so as you go through this, it talks about I2C mode and SPI. But the first, so in 25.2 it goes through SPI, and this is all dedicated to the SPI stuff. It shows you how to hook it up. It shows you the timing and a whole bunch of alternative things you can do. It shows you all the registers for SPI mode. And then you get I2C mode. In I2C mode, well, and I guess in SPI mode too, but for sure in I2C mode, you have your choice. You can use this as a master or a slave. And usually you can pick either one. It talks about the master mode first, and then talks about the slave mode after that. In slave mode, you can assign it whatever slave address you want. In master mode, you don't have an address. The master doesn't have an address. And the interesting thing is there can be multiple masters on the same bus, but the masters cannot talk to each other. But you could have one of your SSI ports set up as a master port for I2C, and you can have the other one set up as a slave port for I2C, and you could then, and that would work fine. You could still, your chip could listen for people that are trying to talk to it as a slave, and then it could take charge and send out information as a master whenever it wanted. And there are ways of deconflicting two masters trying to access the bus at the same time. There's a bus arbitration scheme, and so it's pretty cool the way this is set up. It's a very robust protocol as far as I'm concerned. And I find it a lot easier to use most of the time than SPI. And the reason for that is that SPI has 4 different modes you can use it in. And sometimes it's really hard to get in the right mode. And when you read the data sheet on the device you're trying to talk to, you actually may not know what mode that device is operating in. They may tell you sort of, but the modes are all numbered differently by different manufacturers. And so what might be mode 1 for one manufacturer, it might be mode 3 for another manufacturer. So then you have to go back and look at the 4 options, and we'll talk about that. All right. So let me pull up the slides. And let's see. So I think it's here. Yeah, this will work. This is really easy. Yeah, all right. So, and then I'll go through it a little bit. So, yeah. All right. There's better slides than this, put in here. Rather than spend time. So here's the master synchronous serial port, and there are 2 of them, 1 and 0 on this chip. And then, so the I2C has pretty good, it's a pretty full-featured I2C module. It can be master, it can be slave. In slave mode, it can do byte acking and knacking. And so I'll explain that, but basically what that refers to is whenever you transmit data from slave to master, or from master to slave, there's an acknowledge bit that needs to be sent. but if you didn't get the bits, if for some reason there was a problem with the transmission, then you can excuse me, you can send a NAC, a not acknowledge. Sorry. And if you get a not acknowledge, then you know that the byte you sent to the slave didn't get, so you have to send it again, and vice versa. It doesn't work as robustly for the slave, but if the slave is supposed to send a byte to the master, and the master didn't get it, usually what it does, it just asks for it again. But it is supposed to send an acknowledge bit to the slave. Anyway, so you have the option of sending the acknowledge an ACK or a NAC. There is multi-master support. It's sort of limited, but it's sufficient to actually make it work if it needed to be. And then there is a 10-bit address mode, which I haven't actually seen it used, but most devices that are set up for I2C use the 7-bit mode. And then it can interrupt on stop and starts, so that helps you manage it if you want to set those interrupts up. It has the ability to support clock stretching. What clock stretching involves is when the slave, when the master sends out a data, well, remember that the lines are set up. Well, let me ask you. So how are these lines driven? Does anybody remember? We talked about this at some length. Right. What do we call that? So the lines are pulled high with resistors, and if you look on your board, we did put the pull-up resistors on, and if you look at them, they're right down here. You can see the two little resistors right above my finger, and they're right next to RB6 and RB4. And I used 3.9 K ohm resistors for them, kind of a mid-range. You can run anywhere from 2.5 K or 2 K to maybe 5 K. It depends on how many peripherals you have hooked up. So we went ahead and put on these pull-ups. So why do we need pull-ups? We don't put pull-ups on our other lines, right? Well, we do on our inputs, but normally our lines are driven. It's either high or low when we're using it as an output, right? So how come I put pull-ups on there? Well, what's the deal on those pull-ups? Does anybody remember? So it's right. Go ahead. Somebody was going to take a whack at it? All right. So we call it open collector. All right? And the way open collector, you should put that in your brain and remember. So the way open collector works, the transistors driving the lines are set up like this, and it's usually pulled low, so it's going to be an NPN. So here's the base. So when we turn this transistor on, it's going to pull this line low. When we turn the transistor off, this point's going to float. And so we just put a resistor here. You know, maybe we were using 3.9 K, but you can use values between 2 and 5 or somewhere in there. And so it's good. And this is we're going to pull it up to VCC. So this line then. Everything connected to this bus, and this is the way for the data bus and the clock line. They're both set up like this. So when you want to send information over it, when you want to send a high, you just let your open collector transistor turn off, and you let the line float high by this resistor. When you want it to be low, then you turn your transistor on, and it pulls it low. So you can drive it low, but you cannot drive it high. And that's so that you can have another device also hooked on here. And there's no way you can have a short circuit. If one device is sending to 1, then they're expecting the resistor to pull up the line. If the other device is sending to 0, they're pulling it down to 0. So this point's floating, that point's ground, and this is a 3.9 K to VCC. So there's no problem, right? Everything's cool. We got a little teeny bit of current running through the resistor, and that's it. So it works well for multiple devices where you don't want to worry about, bus contention, something trying to drive at the same time. So what happens then in clock stretching, go high, and then after a period of time, Yeah, with the master, then they pull it low, they leave it low, and then they let it go back high. And then the master, when it lets it go, it expects it to go back high, the master checks it to see if in fact it goes back high. Because if the slave is clock stretching, then the slave may hold the clock low for an additional period of time, and that's the clock stretch. So if the slave says, hey, I haven't quite gotten this stuff, I'm not done yet, locking in your data or sending the data I'm supposed to send, I'll hold it low until I'm ready, and then I'll let it go high. And the master is supposed to detect this. So the master reads its own line and says, well, I let it go high, but guess what? It didn't go high. So when it didn't go high, I know that, and I know the only explanation for that is that this other, one of my peripheral slaves is holding it low. And so that clock stretching feature then is nice, because if the slave is a little too slow to keep up with the rate you're using, then it can stretch the clock when it needs to. It also can detect bus collision, and the whole idea of bus collision is very similar to what I just described. On the data line and the clock line too, if there's primarily the data line, normally when a master starts transmitting, it looks at the lines and it knows if everything's idle, because both lines will be high. And so if it detects both lines are high and it waits for a small amount of time, then it initiates a start signal. And the start signal is taking the data line low when the clock line's high. Normally you only do that when the clock line's low. And so when that happens, then it starts transmitting. Well, if another master starts transmitting at exactly the same time, then there could be a problem, right? Well, the way they detect that problem is every time they send out a high bit, they check and see if the bit goes high. And if the bit doesn't go high, they know that something else is holding the data line low. It must be another master. So they back off and let that master take the bus and run with it. And so even if they've had the exact same bit pattern for a little bit, eventually there'd be a difference in the bits, and then one master is supposed to release to stop transmitting and let the other master take over. And that's how they can have multi-master support. And it's limited. It's maybe not as robust as it could be, I guess. And then we have the ability to do address masking. That's for a slave. So if you set it up for a slave, you can have your chip respond to a range of addresses instead of just a single address. Sometimes you want, as a master, you may want a whole bunch of slaves to respond to a single command, and then other times you want to address each slave individually. Well, so this chip will support that. Now, if your other slaves are hardwired chips like this PCF 8574, then that's not going to work because they don't have that built into them. But if you're addressing, say, 4 or 5 other microprocessors, you can, in fact, build that into them. So one of my friends is building a device to program these little keys that go into a product his company's making, and he wants to program 24 of them at once, or maybe 18. I forget whether it's 18 or 24. And so he's going to use 18 picks to do the programming, and he wants to talk to these picks with the I2C line. So he's going to talk to each of these chips individually with an I2C line, so he can send out a different set of code to each one of the lines, to each one of the picks, and then they can in turn program the little key, which is an I2C programming program. They're going to use the other I2C channel to program these individual little parts, and then they'll verify them, and then they'll send that information back to the master, telling it that, yeah, I programmed it and it's verified. So anyway, it's pretty nice that you can. There might be times there where you might want to address mask, and you might want to talk to all 24 of your picks at the same time, and other times when you want to talk to them individually. Okay, so it'll do all that. Okay, so here's the I2C block diagram. So you see the 2 pins here, and I'm sorry. So here's the block diagram, and you see the 2 pins, and here is the open collector driving those pins. and then of course you have this gate reading the data line, so that it can be, so it can store the data, check for bus collisions and things like that. So anyway, I'm not going to go through this at great length, but basically you normally load up the byte you want to transmit, and then that byte gets shifted out one bit at a time. So this is a true serial port. The bits go out one bit at a time down a single line. And you would think that doing things in parallel would be a lot faster, and in theory I guess it is, but in reality, even your disk drives and your laptops and your desktops use a serial cable instead of a parallel cable. If you take the clock back 15 or 20 years, all the desktop and laptop computers used a parallel protocol with disk drives. And then they've all gone to the serial protocol in the last 10 or 15 years. And I don't know, I'm not sure I understand why exactly, because it is true that parallel is faster. But one of the problems with parallel is if the bits don't travel precisely at the same time down each of the parallel paths, then you have skew at one end and problems. And I have to sneeze again. Sorry, I have a bad cold, but I'm getting better. But anyway, my nose is running like a faucet. But anyway, I know. So, okay, so that's how this works, and it's pretty cool. And you would see, for whatever reason, it turns out that this skew in parallel interfaces causes some real problems. And so you can fine-tune a single wire to run a lot faster than you can 8 wires in parallel. That's, I guess, what turns out to be the case. Sort of surprising to me, but that's how it works, and that's why your disk drive in your desktop or your laptop is a serial device. It's not a parallel device. But the backplane in your desktop and laptop, the so-called PCI bus, it is a parallel bus. So go figure. Anyway, but that bus is pretty tightly controlled. It's not a wire. It's actually a printed circuit board with very careful attention to end termination, and so you don't have to worry about skew so much on that. But you do have to worry about data traveling down a parallel cable at different rates, and when you really try and push it fast, that gets you into trouble, and you can have unpredictable results, and that's why they've gone to serial interfaces. Okay, the memory's still parallel though. All right, so anyway, block diagram. So a typical hookup is like this. So you have an SCL line and an SDA line, and the little X is because you can have SCL1 or SCL2, and then you have a slave out here, which really only has usually one SCL and SDA lines. There actually are some devices. One of the devices, the accelerometer and gyro in the same package actually have typically a little controller built in, and then what they have is a second I2C line that can go out and talk to a magnetometer, and then it has a little built-in processor that can take the magnetometer data and actually process it a little bit and give you a better solution on your accelerometer and your gyro with the magnetometer data. It's really interesting. And so some of these little chips are quite smart, and they actually have some extra I2C going on. The real-time clock chips usually have 2 little packages on that, and you connect it to it with I2C. One package is the real-time clock. It's got one slave address. The other package is a ROM, and it's got another address, and you can store maybe 128 bytes in this ROM if you want, or maybe it's 256. And so you can store some non-volatile information there if you want. All right, like maybe an alarm setting or something like that. All right, so here's some of the terms we talk about. So there's a transmitter and a receiver. There's a master and a slave, and you can have multi-masters. Arbitration, that's when 2 masters sort out who's going to control the bus. I kind of described that. I don't care if you really know about that. I don't think it's very often. Multi-masters are not used that often, really. And then these are synchronous devices. The master sends out a clock. Both devices have the slave device doesn't generate a clock, only the master, so they're all synchronized to the master clock. But there is such a thing as clock stretching that the slave can do. And then when it's idle, you can tell if nothing's going on the bus because both lines will be pulled high. And, and then the slave, then you can have multiple slaves on the bus, but only one typically is addressed at any given time. And so we call that the addressed slave. And that slave will match the address you send out. And again, you can, at least if you're on the slave module on this chip, can mask bits if you want it to, so that you can have multiple slaves responding to the same thing. But this PCF 8574 chip doesn't do that, so you can't do that with all I2C devices, just a few. And then we can either do a write or a read request, and then, but I mentioned clock stretching before on bus collision, talked about that too. All right, so, so a couple of things, and then I'm going to go through the code and sort of talk how this works. So basically, there's two special conditions. You can think of it as three if you want, but really it's just two. And it's a start and a stop. There is also this restart, but the restart is basically the same as a start. It's just that it occurs immediately after the master has completed one transaction. So normally we start everything off by this start condition. And the way the start condition works is the clock line is high and we pull the data line low. Normally you're not allowed to do that. Normally you can only pull the data, you can only change data when the clock is low. And if you think about that, that makes sense because normally the master, remember, because you're using open collectors and the line's pulled high, so the idle condition is the clock line's high. So normally in idle condition you wouldn't expect the data line to get pulled low. So the only time when that happens is when you're issuing a start command. Okay? And then, so when you get a start command, then all the slaves on the bus, it sort of synchronizes them and they know, okay, we need to start paying attention because we're going to get 8 bits of data. And and then we're going to respond. If it's us, if it's my address, I'm going to respond with an active. Okay, so that's a start condition, and a restart condition is exactly the same thing. So the clock is high and we pull the data line low. Same thing. A stop condition is just the opposite. The clock is high and we let the data line go high. So what happens is we hold the data line in, the data line's pulled low already, and then we let it go high during the period of time when the clock is high. Normally we only do that when the clock is low. And again, because the low condition is the active condition, that's why we normally only change the data line during the active condition. So when you want to send out a 1, you would let the data line go high when the clock is low, and then when the clock goes low again, you would, if you needed to send out a 0 now you would pull the data line low. And then the next time when the clock is low, you'd keep repeating that till you send out your 8 bits. So you normally only change the data line when the clock is low. But in a stop condition, we hold the data line low and then we let it go high when the clock is high. That's a stop. And then the start is both lines are high. That's the idle condition. And without pulling the clock low, we let the data line, we pull the data line low. And that's the start condition. It's also the restart. So with that in mind, let's look at the code, and you can see how this works. I think I have slides laid out, but this is better. I'll take a look at the code. So let me do that. Let's see. So I want to do this. Okay. So here's the I2C generic file. So this, you can use this with any I2C device, it would work fine. So the first thing we have is the init program, and the init function. And the init sets everything up. And like I said, it's hardwired for RB4 and RB6 and SP, the synchronous serial port 1, and synchronous, and it programs the CON1 to enable I2C mode in master mode. And then sets up CON2 to pick the right clock frequency and yeah, basically just the clock frequency. All right, and then we use the SSP1 address window. We don't really need that because this is as long as we're operating in master mode, then we don't have to assign an address to our master. But we set that so that it's at the 100 kilohertz rate, and then our slew rate, we set that in our stat. We disable the slew rate and do some other things. So these are the settings we use in our control registers for our synchronous serial port. They'll put it into I2C master mode using our 4 megahertz clock, running at 100 kilohertz rate on the I2C line, and doing some things with the stat register. Okay, then what we do, we have several other functions. So we have a wait function where we wait for the I2C transfer to finish. So once we initiate a transfer, it doesn't finish instantaneously. It takes it a certain amount of time, especially since it's only running at 100 kilohertz. So if we're operating at if our clock is ticking away at 4 megahertz, we can execute a number of instructions before we're going to finish an 8-bit transfer plus a NAC bit. So we definitely need to wait. And so we call the wait function, and that'll keep us from sending in another byte until it's time. So we make sure that these control bits within these configuration and stat registers are set correctly for the next read or write to occur. And then here's where we send a start bit. This is the code for that. And here's where we send a restart bit. There's the code for that. And here's where we send a stop bit. So we have functions that allow us to send start, restart, stop, and wait. And then we have another function that allows us to send out the slave address. Now, this address thing on the slave gets kind of confusing. And that's probably the only really confusing thing about I2C. And the reason it's confusing is because it's a 7-bit address. But how many bits do we send out every time we send out a I2C transmission? We send out 8. So what about that missing bit? What is that all about? Well, the missing bit is added to the address to give us an 8-bit byte to send out. And that missing bit is, obviously it's either a 1 or a 0. And that's going to tell the slave whether the next sequence is a write or a read. And so we have to prep the slave for that, so the slave knows whether it's supposed to be sending data or receiving data. So we append that read-write bit to the 7-bit slave address, and we append it to the low level. So what happens is our slave address gets shifted 1 bit to the left in the process. And so this makes it very confusing, because now, let's say we're using address 27, okay, like our little PCF, whatever it was, 9784. Oh, I never can remember the number. But actually, I can see it on this one. So, yeah, what is it? It's yeah.
8574.
Yeah, 8574. That's what it is. 8574. I don't know why. I just can't remember that. All right. Anyway, so that particular 8574 has the upper 4 bits of the address are hardwired. The lower 3 are set externally, and in this case, they're all set to zeros. So that gives us a hardwired address of 27. Okay. Now, what happens when we and I guess they're hardwired high. Actually, they're hardwired to 1, so that gives us a 27. So here we have 27. So that would normally look like 00100111. Okay, but now we're going to append our read-write bit here, and so now all of a sudden we have 40, 4E or 4F, depending on whether we're writing or reading. So when you read, so here's where the problem comes in. It would be fine if everybody used the same convention, but everybody doesn't. So when you read the data sheet, sometimes they'll tell you, let's say you have a device that you only read, you never write to it except when you write the slave address. So they might tell you, well, you should always use 4E. Well, are you supposed to shift that and append the read-write bit? or is that supposed to be the actual address, or what the hell's going on? And you don't really know. It's just can be very hard to figure it out. So in this case, the 27 is the unshifted 7-bit address. So there's actually 2 addresses for this part, 4E and 4F. 4E would be the write address and 4F would be the read address, or maybe vice versa. I get confused about that too. But in any event, it's confusing. So always remember that you have to be on the alert for whether you need the 4-bit, whether you're getting the 7-bit unshifted address of the slave, or whether you're getting the shifted address with an appended read-write bit. And you have to read carefully. And then, just to make matters particularly irritatingly problematic, let's say here's your data sheet, and let's say it's 20 pages. So, and you kind of know what you're doing, and you've got your code more or less written because you stole it from someplace or whatever, and all you want to do is go get the slave address so you can put in there. And guess what? Here's where they put the slave address. 18 pages down in a little footnote. And it just really cheeses you off, because they ought to put it up here, right at the very beginning, where it would be easy to see it. No, they don't do that. They make you read through the whole dang thing until you get to that part, and then they even there kind of obscure it, and they probably put it in a table of several other parts, and then you're not even sure which table entry refers to your part. And then you have to go dig your chip up and look at the additional numbers on it. In this case, 8574A has a different set of addresses. So you have to pay attention to which it is. Yeah?
So can I2C ever be full duplex, or is it always half duplex?
So it's never full duplex. It's always sending information one way or the other. And usually because you have a master-slave relationship, the master always has to send out the slave address, and then it can do multiple reads. But it has to first send out a slave address with a read bit appended, and then the slave knows it's supposed to keep reading. And usually they're set up so if you keep reading, it'll keep sending you information. A lot of accelerometers use I2C, and that's how they typically work. A lot of times the accelerometers have more than 8 bits of information. So you read once, you get the lower 8-bit data. You read again, you get the upper X data. You read again, you get the lower Y data. You read again, you get the upper Y data. You read again, you get the lower Z data. You read again, you get the upper Z data. And it automatically increments for you. But you can, I think a typical accelerometer probably has 30 configuration registers in it. And so if you want to, you can screw around with it and change things. And part of that is because they have a couple of interrupt lines you can set up. And like for instance, maybe you want to use the chip. Maybe you want to put this in a maybe like back in the days when we had the little things that you put all your MP3s on and you listen with headphones, and they had like thousands of them. But it was before we had all the solid-state drives, so they actually had no kidding, a small disk drives in them with the disk actually spinning. And so some of those might have an accelerometer built in so that if it detects itself falling, then it will unload the heads and try not to screw the disk up. Because obviously people, kids would drop those all the time. So anyway, so there's special things like that. And most of these devices have all these extra registers. They just drive you insane. But usually they make it so that if you just use the default start point, they work pretty well for most purposes. But like for instance, if you're doing so let's say you're using an accelerometer to stabilize the image. So how many of you have cameras that are motion stabilized? Yeah, they use an accelerometer. That's how they do it. And the shutter, when you punch the button, doesn't really take the picture. You punch the button, and then the microprocessor in there looks at the accelerometer data, and when it detects it's within a certain range of variation, then it clicks the shutter. And so it actually does it using accelerometer data. Pretty cool, right? And so you can actually have an interrupt set up with those criteria that interrupts it and drives the camera shutter, so you don't have to sit there and process it. That happens in the actual accelerometer, or potentially it can. So these devices, and of course manufacturers are competing against each other for functionality, and so they just load these things up with all these features, trying to get more sales, which then make it really hard for somebody who's not interested in these other features to actually make sure they don't turn on some of these bogus features, not bogus, but some of these extra features they don't really need accidentally and screw up all their data. All right, well, you get the idea. Okay, so anyway, so before you do anything, you have to send out this this address, and that's so you can tell which slave needs to respond. All the slaves that are out there listening to this, and they're checking their built-in hardwired addresses against the address you're sending out. And if they match, then they send an acknowledge, and they pay attention to that read-write bit to know whether or not they're supposed to go into read mode or write mode. And then if they're supposed to go into write mode, hopefully they know what they're supposed to write. What they're supposed to, read mode. If the master goes into read mode, the slave is supposed to write. And so hopefully they know what they're supposed to write. And of course you typically have to set this up. And usually what you have to do is you, like on the accelerometer, first you send out the address and a write bit, and then you write out the register you want to start reading. In this case, it's register 1. Register 0 is a control register, so you want to screw around with the device, you write a 0, and then you can adjust the registers. But if you just want to read the 6 position registers in the accelerometer, you write out a 1, and then you send out a restart, and you send out the slave address again with a read bit appended, and then you do 6 reads in a row. And the slave is supposed to be smart enough to send you the register 1, 2, 3, 4, 5, 6 in that order. And that's how you get the data. And it sounds like it's really a lot of work, and it kind of is when you're first trying to understand it. But once you kind of get it working, it tends to work really well. And it's pretty reliable communication. And also because normally you're just talking between one integrated circuit and another integrated circuit on the same printed circuit board are very close to each other with just a very short cable. So it's not one of those protocols where you can go across the room with it. That's not the intent at all. Okay, so that sends out the address and appends the read or write bit. Okay, and then we have I2C read. So this actually reads a byte. So notice how this works. So the first thing you do is you wait until the line's not busy, and then you set this receive enable bit, and then you wait again to make sure that's all checked off, and then you read the data. Well, yeah. So what you do is you do the wait, and then you issue the read. So your I2C module actually goes through the process of reading all 8 bits and the acknowledge bit, or sending out the acknowledge or not acknowledge automatically. That all happens for you. And then when it sets this RC bit, then you know it's done, or you wait till that's done, and then you read the data in the buffer. So it'll actually take the 8 bits it read serially, buffer them up into an 8-bit buffer, and then that's what you read to get the data. And then you wait a little bit longer, and then you acknowledge or you don't acknowledge, and then you send out the acknowledge sequence if you're going to acknowledge, and then you're done. Let's see, there should be a write thing. Maybe I screwed it up. Oh, there's the write. So here's the write. So to do the write, it's a little easier. You just you wait till it's not busy, and then you load the buffer with data, and that initiates a write sequence. Okay. So yeah, this didn't really show what I wanted to show. So if we then look at the I2C_LCD file, this gives us a little better feel for how this actually happens. Okay, so this is is this the C file? Yeah, sorry. So I actually. So if we do this file, so what this does then, there's a function here that reads the busy bit, and so we actually put the I2C, the LCD module into a write mode, and we actually have it not talking directly to the LCD. We're talking indirectly to the LCD. We're talking directly to the PCF 8574 through the I2C protocol, and the 8574 is talking directly to the LCD through a parallel protocol. And so we have to kind of keep everything straight. And so we do have to write it out, the data we want to send, plus we have to leave the data in place, but toggle the bit that's actually controlling the E line. And so you have to figure out, well, which bit's toggling the E line. And actually, I don't remember off the top of my head. I don't remember if I said that at the top. Yeah, I don't think I did. And then if you have a different one of the interfaces, now you have to use the reverse protocol where they have a different bit that controls the E line. So it gets kind of crazy, but anyway, so basically what we're doing is sending out 30 or 3x once, twice, 3 times, then we put it into 4-bit mode, and then once we're in 4-bit mode, now we have to send out 2 nibbles every time we want to talk to it. And again, remember, our PCF 8574 chip is talking to the LCD in 4-bit mode. But the 3x, 3x, 3x we're sending out is 8-bit mode, even though 4 of the bits are not connected. And so anyway, so we do that, and then we put it in 4-bit mode, and then we turn it on and set the cursor to blinking underline, and then we set it to go to the low byte, and by sending out that command, so we're sending that out, and you can see, so we do I2C write, I2C write, I2C write, we check the busy bit, and then we send out the stop bit, and then we're done, more or less. So we don't have to check the busy bit between these writes, but we do when we write a command to move the cursor, to underline, to home it. That makes it, that particular command can take up to 1.4 milliseconds, so we definitely have to check the busy bit for that one. Anyway, and so here you have this command, I2LCD position, so we can set the cursor wherever we want to start writing text at that location. And so it goes through this routine to do that. And then here's a write command where we're going to write a whole string. So we're going to do this until we get to a null character. Or actually, they're going to send us a character max, so they're actually going to send us a count. And they give us a pointer and a count. So we use the pointer to access the data, and we send it, we scroll, we increment through it the number of times of the character max. And so that's what we do there. And then here's a I2C command. So now we can send a command to change the cursor for a different type, or to change our format, or whatever, number of different things. Change it from auto increment to decrement, or we can scroll the display. There's a lot of different things you can do with it. And this sends out the command. One of the things it does, it sends out the bits that control the RS bit, and make sure that that's set correctly, so it's now set for command. Whereas when we're writing data up here, or a string, we want the RS command as a 1, otherwise we want it as a 0 for commands. And you can see we send out the start bit, we send out the slave address with an appended write bit, and then we write, then we do the write operation, and then we check the busy bit, and then we send the stop bit. So you actually have to send the start bit, you have to send the slave address, you have to have appended the write bit or the read bit, and then if it's reading, then you can start reading. But if you're going to write first and then read, then you send out the write bit, then you write what you're going to write, then you send out the slave address again with a read bit, and you do a restart before you do that, then you send out the slave address with a read bit, and then you do several reads, and then you do a stop bit. And the nice thing, the one nice feature is you can keep reading multiple times. That's legal. But once you send the stop bit, then you have to send another slave address with a read or write bit appended and all that, and another start bit too. So there's definitely some protocol to the I2C. All right, we'll take a few minutes and look at SPI. And let's see. here it is. Okay, so SPI. So there's a bunch of examples in here. I'm not going to go through them all. I just want to give you the basics. So the big differences between I squared C and SPI. So I want you to know the differences. I just want you to know, the 20,000 foot differences between these two protocols. Okay, 20,000 foot differences. So I squared C is slow, but you only use 2 wires, and you can have lots of peripherals on the same bus. SPI is fast, but you use more wires because not only do you need a data line and a clock line, but you need 2 data lines, one going one way and one going the other because you travel both ways simultaneously. So you need a clock line, a serial data out, a serial data in. Sometimes we call the serial data out the MOSI, master out, slave in, and we call the serial data in MISO, master in, slave out. I really prefer MISO and MOSI because if you have 2 devices and they're labeled MISO and MOSI, then what's really nice is you can connect the MOSI to the MOSI and the MISO to the MISO. So that's really nice. Just like in I squared C, you can connect SCL to SCL and SDA to SDA. But if they use SDO and SDI, now you need to switch them over. Now you need to cross them. And that's drives you crazy. And then what's really bad is if one's labeled MOSI and the other MISO, and the other's SDO and SDI, then you have to scratch your head and figure out what it is. Well, MOSI is master out, slave in, so that would be SDO. So that would go to the SDI. And MISO is master in, slave out, so that would be the serial data out from the slave. This is the master and that's the slave, so that would be crossed over again. So it's really nice if they use MISO and MOSI, but unfortunately, apparently, somebody copyrighted those, and so a lot of people don't use them because they don't want to get in trouble. Is irritating, but that's the way it is. In addition then, you have the clock line. Now the good news is the clock line connects to the clock line. So that's good. And the master is the only one that generates clocks. There's no screwing around with the clock. The slave can't do any clock stretching in SPI. And these lines are not open collector, they're hard driven. So that's why you need a slave select. So if you have a master and 2 slaves, then guess what? On the serial data outline from the slaves, you have to tri-state those lines with the slave select line. So if your slave is not selected, it must tri-state its lines. Otherwise, one slave would be sending out highs and lows, and another slave would be sending out lows and highs, and they'd have short circuits on the bus. So that's not going to work. So they definitely have to tri-state their serial data outline if they're not the addressed slave. So what that means then is, for a single slave, you need 4 wires. And then if you add another slave, you have to add an additional slave select line for that slave. So now you need 5 wires, and for every additional slave, you have to add another slave select line, in theory. Now there are ways of getting around it, but in theory, that's how that's normally supposed to work. And it turns out the slave select is not necessarily controlled by the module itself. Usually, your software has to handle the slave select lines on its own. So the module, some of the things that would be taken care of, say, automatically in the I squared C world, you have to do maybe somewhat manually in the SPI world. But the real advantage is the SPI is faster. It can go at megahertz rates. And you exchange data, it is full duplex. But I will tell you, it's rarely used as full duplex, because usually you're not interested in sending data to the master and getting data from the master at the exact same instant. Normally you have to send data to the slave, and then the slave decides what data to send to you, and then you do another one. So most of the time, when you talk to the slave, either the slave or the master is sending dummy data is going one way or the other, and real data is going the opposite way. So typically, you're not taking advantage of the full duplex feature. But you could, in theory, do that. It's just that it's rare that it works out that it's possible. Okay, so like I said, there are 4 modes. And the 4 modes are based on the sampling edge and how the clock idles. So if the clock, so we talk about mode 0 is the clock idles low and we sample on the rising edge. The mode 1, and again, not everybody defines these the same way, so there's really no point in going through it. But mode 1 would be the clock idles low, but you sample on the falling edge. And then, mode 2 and mode 3 have the clock the opposite, sampling low and high again. So, because of these 4 modes, you can really pull your hair out trying to get in the right mode. And, okay, so yeah, you could look at the timing diagrams, but those are kind of tedious, especially when there's pages of them, and the explanations aren't as obvious as it is in this drawing. So, and like I said, a lot of people define these modes differently. They may or may not all agree that mode 0 is the same. This one considers mode 0 to be clock idling low, sampling on the rising edge. That may not be mode 0 in another manufacturer's parlance. So we normally use SPI to interface shift registers, or things that want to move data fairly quickly. This would be high-speed A to D or D to A converter chips, like in a if you have like something playing a CD disc and you're listening to it with headphones, it's probably got an SPI interfaced A to D chip and D to A chip built into it. The master initiates all the transfers, and it generates the clock. And so it is considered duplex, but like I said, it rarely is used as a duplex transmission. So usually you're sending dummy data one way, and then real data the other way. Okay, so this is what a transfer looks like. The slave select goes low, and the clock starts ticking away. Normally, when you're not transmitting data, the clock isn't ticking, and then the data starts getting shifted. The data from the master slave shift register is shifted down the serial data outline, or the MOSI, into the slave's serial data inline, or its MOSI, and then the data is shifted out of the slave, out of its serial data outline, or out of its MISO, into the master's MISO, or the master's SDI. So, because of the nomenclature, you have to be careful what you hook up to what you hook up. Anyway, when that's all done, you go 8 times, and you're done. You've now shifted 8 bits from the slave to the master, and 8 bits from the master to the slave. And maybe only 8 of the bits of the 16 bits are meaningful. And that's how they transfer. There is a bidirectional mode where you can shift data over one line both ways. I don't think anybody uses that. It's super rare. And you can do multiple slaves. One way to do multiple slaves is with, well, here you have a single slave, and you just ground the slave select, and you don't actually have to use the slave select. But here you have 3 slaves. Each slave has its own slave select line. So now you have the 4 lines plus 5, plus another, so that's 6 lines altogether. And then in some cases, you can do this daisy chain thing, where you have the MISO, the MOSI connects to the MOSI, the MISO connects to the next MOSI, and so forth, and the final MISO connects to the master MISO. And what you do is, you have to shift out 8 bits 3 times to get it to the slave, the K, well, the 3rd slave, and then the information from slave 0, you have to shift 3 times to get the information, say, from slave 0. So it does lengthen the time it takes to get the data exchanged. And you have to keep track of how far, how many shifts away your slave is. But you can do this. It might not work for everything, though, but you can do it for some things. Okay, anyway, I don't think I'll go through any of this. Any questions about SPI or I2C? Everybody good? All right, we'll see you in lab tomorrow.